The dawn of June 6, 1944, marked the beginning of the largest amphibious invasion in human history. Operation Overlord, the D-Day landings, saw hundreds of thousands of Allied troops storm the beaches of Normandy, launching the long-awaited liberation of Western Europe. The bravery and sacrifice on those beaches are etched into the annals of history, a testament to courage against overwhelming odds. But even as the first waves of soldiers fought for every inch of sand, a problem of colossal scale loomed, a logistical nightmare that threatened to derail the entire invasion and bring the advance across Europe to a grinding halt. This challenge wasn't about bullets or bombs, tanks or planes. It was about something far more fundamental, something without which no modern army could fight for even a single day: fuel. The sheer scale of the Allied war machine, poised to sweep across France and into Germany, demanded an astronomical amount of petroleum products. Millions of men, tens of thousands of tanks, trucks, jeeps and aircraft, all consumed fuel at an insatiable rate. To sustain a rapid decisive advance deep into enemy territory, the Allied forces would need an uninterrupted supply of gasoline, diesel, and aviation fuel, not just thousands, but millions of gallons every single day. Yet, the very nature of the amphibious invasion meant that readily available deep-water ports, essential for unloading vast quantities of fuel from tankers, would not be immediately captured. The heavily defended ports like Cherbourg and Le Havre were expected to fall only after fierce fighting, and even then, German demolition teams would undoubtedly render them unusable for weeks, if not months. For German intelligence, this logistical bottleneck was perceived as the Achilles heel of the entire Allied invasion strategy. Their high command believed, with good reason, that without secure and functioning ports, the Allied armies would quickly run out of steam, tethered to the beaches by their colossal thirst for fuel. They calculated that any deep penetration inland would be impossible, forcing the invaders to consolidate their gains slowly, vulnerable to counterattack. The logistical hurdle was, in their eyes, an insurmountable barrier, a fatal flaw that would ultimately condemn the Allied invasion to failure. But even as the storm gathered over the English Channel, a secret, audacious plan was already being conceived and brought to life, a testament to wartime ingenuity that transcended the conventional battlefield. This was a project born of absolute necessity, shrouded in the deepest secrecy, and pushing the boundaries of engineering to its very limits. It was a solution that aimed to defy geography, bypass enemy defenses, and provide an invisible lifeline directly beneath the waves. This was PLUTO, pipelines under the ocean. This wasn't about a single weapon or a famous battle, but a staggering feat of design, manufacturing, and deployment that would pump the lifeblood of the Allied advance directly from England to the battlefields of France. It was a project that, if successful, would utterly baffle German intelligence, leaving them to wonder how the Allied armies continued to advance with such relentless speed, seemingly without conventional supply lines. The story of PLUTO is a testament to the quiet heroes of engineering and logistics, the unsung innovators who ensured that the great invasion of Europe, once launched, would never run dry. This audacious gamble, kept secret for years, was about to prove that victory wasn't just won with bullets and bombs, but with unseen ingenuity beneath the waves. The sheer, staggering volume of fuel required to prosecute a modern, mechanized war was a concept that few outside the highest echelons of military planning truly grasped. For Operation Overlord, the scale was unprecedented. Millions of Allied soldiers were not just men with rifles. They were elements of a vast, interconnected machine. Each Sherman tank, each M4 half-track, every jeep, truck, and reconnaissance vehicle, every Spitfire, Mustang, and Thunderbolt fighter bomber that would support the ground troops, demanded a constant, voracious supply of petroleum. It wasn't just about moving troops, it was about powering an entire mobile nation at war. Estimates for the fuel consumption during the initial phases of the invasion were astronomical. Once ashore, an advancing army would require millions of gallons of gasoline for its vehicles, high-octane aviation fuel for its air cover, and diesel for its heavier equipment, all flowing ceaselessly. A single armored division on the move could consume hundreds of thousands of gallons in a single day. Without this constant flow, the momentum of any advance would immediately falter, vehicles would become static targets, and the hard-won beachheads would become death traps for an army that could neither move nor fight. Traditionally, supplying such an immense quantity of bulk liquid fuel to a continental landmass relied on deep-water ports. Giant oil tankers would sail across the ocean, dock at purpose-built facilities, and unload their cargo directly into storage tanks and then into distribution networks, pipelines, rail cars, and tanker trucks. This method was efficient, tried and true, and utterly indispensable for large-scale operations. However, the very nature of the D-Day invasion presented an insurmountable obstacle to this conventional wisdom. The Normandy coast, chosen for its strategic advantages in secrecy and geography, lacked major deep-water ports suitable for immediate large-scale offloading. The nearest significant ports, like Cherbourg and Le Havre, were heavily fortified by the Germans. Allied planners knew that these strongholds would not be captured easily, and even once they fell, they would be subjected to systematic and extensive demolition by retreating German forces. Bridges would be blown, port facilities wrecked, cranes toppled, and harbors mined and blocked with sunken ships. It could take weeks, or even months, for Allied engineers to clear and reconstruct these crucial facilities to handle the required volume of fuel. The implications were dire. If the Allied armies were forced to wait for port reconstruction, their rapid advance would be impossible. They would be confined to a narrow, vulnerable beachhead, constantly under threat from German counterattacks, losing the element of surprise and momentum. The entire invasion could grind to a halt, or worse, be pushed back into the sea. The logistical tale of the invasion, particularly its fuel requirements, represented a staggering vulnerability. German intelligence, always keen to identify Allied weak points, understood this fundamental problem perfectly. They had meticulously studied the requirements for large-scale invasions and concluded that sustained operations across the Channel without functioning ports were simply not feasible. High-ranking German officers, including Hitler himself, believed that the Allies would eventually run out of fuel, becoming bogged down and vulnerable. They saw this as a built-in, unshakable defense mechanism, a guarantee that even if the Allies managed a landing, they could never achieve a decisive breakout or a deep advance. This conviction heavily influenced their defensive planning and their expectations for the inevitable Allied failure in the post-landing phase. Against this backdrop of seemingly insurmountable logistical hurdles and confident enemy predictions of failure, the need for a radical, unconventional solution became paramount. Conventional methods were a dead end. The entire invasion hinged on finding a way to deliver fuel continuously and immediately without relying on conventional port infrastructure, a challenge that would demand unprecedented engineering ingenuity and unwavering secrecy. The stage was set for a solution so audacious that German intelligence couldn't even conceive of it. Faced with a logistical dilemma that threatened the very viability of the liberation of Europe, Allied planners, particularly the British, knew that conventional solutions were insufficient. The capture and repair of ports would be too slow, and the constant shuttle of vulnerable fuel tankers to beachheads would be too dangerous and inefficient. A truly radical idea was needed, one that could bypass these obstacles entirely, delivering fuel directly and continuously to the invasion forces. This audacious concept was born from a fundamental understanding of what a pipeline could achieve: a continuous, high-volume flow of liquid, impervious to many surface threats and independent of port infrastructure. The man credited with championing the core idea was Vice Admiral Lord Louis Mountbatten, then Chief of Combined Operations, who famously suggested in 1942, "Why not pump it all the way?" This seemingly simple question ignited a monumental engineering challenge. The idea of laying an oil pipeline across the English Channel was not entirely new in wartime discussions, but its practical implementation, given the scale, urgency, and secrecy required, was unprecedented. The project was given a deceptively innocuous codename to mask its true purpose: PLUTO, pipelines under the ocean. The core concept of PLUTO was breathtakingly simple in its objective, yet incredibly complex in its execution: to lay flexible, submarine pipelines directly across the English Channel, connecting existing British fuel depots to the Allied beachheads and, eventually, to the rapidly advancing armies in France. This would create an invisible lifeline, a continuous umbilical cord of petroleum beneath the waves, impervious to aerial bombing, U-boat attacks, and the devastating German demolitions awaiting captured ports. The engineering challenge was immense. Standard rigid pipelines, used on land, were clearly unsuitable for laying across a dynamic seabed in wartime. They would be too fragile, too difficult to install quickly, and susceptible to damage. What was needed was a flexible pipeline that could be manufactured in vast lengths, coiled, and then unspooled directly onto the seabed, much like a giant undersea telephone cable. This was where the genius of several British engineers, particularly the work of Clifford Hartley and his team at the Anglo-Iranian Oil Company, later BP, came into play. They proposed two primary designs, both revolutionary. The HAIS, Hartley Anglo-Iranian Siemens, cable. This was essentially a lead pipe, reinforced with layers of steel tape and steel wire armor, similar in construction to a submarine telegraph cable but designed to carry liquid fuel. It was robust, flexible, and could be produced in continuous lengths. The Hamel pipe, developed by the engineers H. Hammack and B. Ellis at the National Physical Laboratory, this was a steel pipe with a much larger diameter, 3 inches compared to HAIS's 2 inches, making it capable of carrying significantly more fuel. Its genius lay in its construction. Sections of pipe were continuously welded together into very long lengths, which were then coiled onto enormous floating drums, looking like colossal cotton reels. The development and testing of these pipelines proceeded under the highest possible security. Everything about PLUTO was a closely guarded secret, a vital component of the overall D-Day deception plan, Operation Fortitude. Work was undertaken in isolated, disguised locations. Factories producing the pipes operated under intense scrutiny, their output disguised as other mundane war materials. Even the workers involved were often unaware of the ultimate purpose of their labor, told they were manufacturing parts for bog roll or other innocent items. The goal was to keep German intelligence completely in the dark, allowing this audacious project to unfold entirely by surprise. The stakes were astronomical. If PLUTO failed, if the pipes proved too fragile, too difficult to lay, or if the Germans even suspected its existence and targeted it, the entire invasion could be crippled. But if it succeeded, it would negate the greatest logistical challenge of D-Day, providing the fuel that would literally drive the liberation of Europe. The audacious answer to the logistical nightmare was not merely a pipe, but a symbol of Allied ingenuity and determination to overcome any obstacle, seen or unseen. From its very inception, Project PLUTO was cloaked in a veil of absolute secrecy, a clandestine endeavor born of necessity and maintained with an intensity comparable only to the Manhattan Project. The British and American high commands understood that the success of the entire D-Day operation, and the subsequent advance into Europe, hinged not just on the technical feasibility of the pipelines, but on the Germans remaining completely ignorant of their existence until it was too late. Any hint, any leak, any discovery by Axis intelligence could have catastrophic consequences, leading to countermeasures that would render the entire audacious plan moot. The need for secrecy permeated every aspect of PLUTO. The very codename, Pipelines Under the Ocean, was itself a masterstroke of ambiguity, allowing casual mentions to sound like innocent, if ambitious, engineering projects, rather than a war-winning strategic gambit. This was part of a broader, elaborate deception plan known as Operation Fortitude, designed to mislead German intelligence about the true location and scale of the D-Day landings. PLUTO was a crucial, hidden component of this larger illusion. Work on the specialized pipes, both HAIS and Hamel, took place in various factories across Britain, but under conditions of extreme compartmentalization. Workers involved in manufacturing the innovative lead-sheathed HAIS cable were told they were producing components for a new type of submarine telephone cable. Those fabricating the continuous steel Hamel pipe were often given equally vague or misleading explanations, sometimes informed they were making parts for bog roll, toilet paper, or components for general utility infrastructure. This deliberate obfuscation meant that no single individual, outside a tiny inner circle, had a complete picture of the project's true nature or ultimate destination. Loose talk was strictly forbidden, and the penalty for security breaches was severe. Even the testing of these revolutionary pipelines was conducted in remote, carefully selected locations to avoid detection. Sections of the HAIS cable were tested in a Scottish firth, far from prying eyes, while the colossal conundrums, the floating drums designed to lay the Hamel pipe, were developed and trialed in secluded bays, disguised or camouflaged when not actively in use. The scale of the conundrums alone, each a massive bobbin capable of holding up to 70 miles of pipe, would have been a dead giveaway if observed by enemy reconnaissance. The communication networks associated with PLUTO were equally secure. Reports, plans, and technical specifications moved through highly classified channels, often hand-delivered by trusted couriers. The number of people with full knowledge of the project's scope was kept to an absolute minimum. German intelligence, ever vigilant, certainly monitored shipping traffic in the channel and meticulously analyzed Allied logistical patterns. They were looking for signs of massive fuel buildups, new port constructions, or unusually heavy tanker traffic. Their analysis correctly identified the fuel supply as a major challenge for the Allies. However, their assumptions were entirely based on conventional methods of fuel delivery. The idea of a continuous underwater pipeline, circumventing all traditional port infrastructure, simply did not factor into their calculations. It was a concept so far outside their perceived possibilities that it bordered on science fiction for them. This profound oversight was PLUTO's greatest strength. German intelligence, confident in its assessment of Allied logistical limitations, dismissed any fleeting rumors or anomalous observations as irrelevant or impossible. Their preconceptions about what was achievable under wartime conditions, particularly by their technologically inferior enemies, as they often viewed them, provided a crucial blind spot. The extreme secrecy around PLUTO wasn't just about tactical surprise. It was about protecting a strategic vulnerability that, if exposed, could have directly led to the failure of the entire European campaign. By remaining an invisible lifeline until after the invasion was firmly established, PLUTO would allow the Allied armies to achieve the momentum and penetration that German planners believed impossible, fundamentally altering the course of the war on the continent. The grand deception would soon be revealed, not by words, but by the relentless advance of tanks fueled by a silent, unseen river of petroleum beneath the waves. The audacious concept of PLUTO demanded an unprecedented feat of engineering and manufacturing. Simply conceiving of an underwater pipeline was one thing. Actually building and deploying it under wartime pressure across a hostile channel was an entirely different magnitude of challenge. The core problem was creating a flexible, robust pipe that could be mass-produced in immense lengths, withstand immense internal pressures from pumping fuel, resist the corrosive effects of seawater, and survive the stresses of being laid on an unpredictable seabed, all without revealing its purpose. British engineers, leading the charge, tackled this problem head-on, developing two distinct and revolutionary pipeline designs. The HAIS cable, a pipeline masquerading as a cable. The first design, known as the HAIS cable, was the brainchild of Clifford Hartley of the Anglo-Iranian Oil Company. Its genius lay in its adaptation of existing technology. Hartley realized that the construction of a submarine telegraph cable, designed to be flexible, strong, and watertight for undersea communication, could be modified to carry liquid fuel. The HAIS cable was essentially a 2-inch diameter lead pipe, carefully extruded. This lead core was then reinforced with multiple layers: impregnated paper insulation, cotton tape, layers of galvanized steel tape, jute servings, and finally, a heavy outer layer of steel wire armor. This intricate construction gave the pipe incredible strength, flexibility, and resistance to external damage, allowing it to be coiled and unspooled without kinking or collapsing. The HAIS cable could be manufactured in continuous lengths of up to 30 miles, a feat in itself. The Hamel pipe, the steel serpent. While HAIS was effective, a second, larger capacity design was developed to increase the volume of fuel that could be transported. This was the Hamel pipe, named after its inventors, H. Hammack and B. Ellis from the National Physical Laboratory. The Hamel pipe was a 3-inch diameter steel pipe, a far more challenging material to make flexible in long sections. Its innovation lay in its method of construction and deployment. Individual sections of steel pipe were continuously welded together on giant production lines, creating incredibly long, unbroken lengths. These lengths, far too rigid to coil onto a conventional ship, were instead wound onto enormous floating spools, or bobbins, that looked like colossal cotton reels. These specialized drums, known as conundrums, were some 60 feet in diameter and 30 feet wide, each capable of holding up to 70 miles of pipe. The challenge of laying the pipes. Manufacturing the pipes was only half the battle, laying them was another monumental task. Specialized ships were required for each type. For the HAIS cable, converted cable-laying ships, like the venerable HMS Holdfast, formerly a merchant cable layer, were repurposed. Their vast internal cable tanks were ideally suited for coiling the flexible HAIS pipes, and their experience in precision seabed laying was invaluable. For the Hamel pipe, the conundrums themselves became the laying vessels. These massive drums were towed across the channel by powerful tugs, slowly rotating as they unspooled the continuous steel pipe onto the seabed. This method allowed for incredibly rapid deployment, laying miles of pipe in a matter of hours. The precise navigation of these towing operations, often under cover of darkness or poor weather, added another layer of complexity and secrecy. The sheer scale of the manufacturing effort was immense. Factories across Britain worked around the clock, producing thousands of miles of these innovative pipelines. Every step, from the extrusion of lead to the welding of steel, had to be perfected and performed with unwavering quality control, as a single weak point could lead to a catastrophic rupture under pressure. The weight of the materials, the precision required, and the unprecedented nature of the task pushed the limits of wartime industrial capacity and engineering ingenuity. This was engineering on a grand, audacious scale, not building bridges or ships in the conventional sense, but creating an entirely new form of transportation infrastructure, hidden from the enemy and capable of sustaining an entire invasion force. The successful development and mass production of the HAIS and Hamel pipes, along with the specialized means to lay them, were crucial steps in transforming PLUTO from a daring concept into a tangible, war-winning reality, a silent testament to the hidden heroes of industry and innovation. With the revolutionary pipelines designed and under mass production, the next critical challenge for Project PLUTO was to establish the infrastructure that would actually pump the millions of gallons of fuel across the English Channel. This required a robust network of pumping stations on the British coast and a dedicated, highly specialized naval task force to lay and maintain the undersea arteries. This entire operation, code-named Force PLUTO, was an intricate dance of engineering, logistics, and naval precision, all executed under the impenetrable veil of wartime secrecy. On the British side, the crucial pumping heart of PLUTO was established at several strategically chosen locations, primarily at Sandown on the Isle of Wight and Dungeness on the Kent coast. These sites were selected for their proximity to the shortest crossings of the Channel, their relatively sheltered conditions, and the ability to disguise the massive construction work required. These weren't ordinary fuel depots, they were elaborate, high-pressure pumping stations, designed to force petroleum through miles of underwater pipeline. The engineering behind these pumping stations was itself a marvel. They housed powerful, specially adapted piston and centrifugal pumps, capable of generating the immense pressure needed to overcome the resistance of long, narrow pipes running along the seabed and then upwards onto the French coast. The sheer volume of fuel required meant that these stations had to operate continuously, often at maximum capacity, for months on end. To minimize the risk of detection by German aerial reconnaissance, the stations were ingeniously camouflaged. Pumping equipment was often hidden in disguised buildings, made to look like old garages, seaside bungalows, or even ice cream parlors. Tanks were buried or heavily netted, and the entire area was carefully managed to appear innocuous to any passing enemy aircraft. Once the fuel was ready to be pumped, the pipelines themselves had to be laid. This was the responsibility of Force PLUTO, a dedicated naval unit comprised of converted merchant ships, tugs, barges, and the specialized cable-laying vessels for HAIS, and the mighty conundrums for Hamel. The men of Force PLUTO, a mix of Royal Navy personnel, merchant Navy sailors, and particularly the skilled engineers of the 55th Company, Royal Engineers, who were instrumental in the pumping operations, faced immense pressures. They operated in the treacherous waters of the English Channel, known for its strong currents, unpredictable weather, and the ever-present threat of German patrols, mines, and air attacks. Despite the secrecy, the act of laying miles of pipe was inherently visible, making the timing and methods of deployment critical. The process of laying the pipelines was meticulously planned. The HAIS cables, once coiled in the vast holds of cable-laying ships like HMS Holdfast, were slowly unspooled onto the seabed. This required precise navigation and constant monitoring to ensure the pipe was laid smoothly, avoiding kinks or snags that could compromise its integrity. For the Hamel pipe, the gigantic conundrums were towed by tugs, steadily rolling and deploying the continuous steel pipe. The scale of these operations was enormous, Each crossing could involve multiple pipelines, laid in parallel or in close succession, to ensure redundancy and maximum throughput. The successful laying of a pipe wasn't the end of the challenge. Once on the French side, the pipes had to be brought ashore, secured, and connected to temporary distribution networks. These receiving terminals were often hastily constructed and equally well camouflaged, designed to quickly channel the incoming fuel into mobile tanker trucks or into rapidly constructed forward pipelines leading to tactical depots closer to the front lines. The entire system had to be robust enough to withstand the rigors of battle, yet flexible enough to adapt to the fluid nature of the Allied advance. The strategic vision was clear. By creating multiple redundant pipelines, the Allies would establish an invisible lifeline immune to the conventional methods of interdiction that Germany expected. It meant that the liberation armies would not be held hostage to the fate of a single port or a vulnerable surface fleet of tankers. This vast, pulsating network, from the hidden pumping stations in England, across the seabed, and onto the battlefields of France, was designed to be the continuous supply of liquid energy that would allow the Allied armies to outrun, outmaneuver, and ultimately overwhelm the German defenses. The pumping stations were the heart, and Force Pluto were the hands, bringing this audacious vision to life, ready to fuel the unstoppable momentum of the invasion. The monumental effort of designing, manufacturing, and planning Project Pluto culminated in the tense days following D-Day. While the initial landings on June 6, 1944, focused on securing beachheads, the logistical clock immediately began ticking. The need for fuel was urgent and intensifying by the hour. German intelligence, as anticipated, had ensured that the captured deep water ports were rendered unusable. Cherbourg, a vital prize, would not be fully operational until months later. The Allied advance, therefore, depended entirely on innovative solutions for resupply. Pluto was designed to answer this immediate and critical need. The first pipelines, code-named Tombolas, were specifically engineered for rapid, temporary deployment directly onto the invasion beaches. These initial, shorter routes aimed to connect directly from tanker ships anchored offshore to receiving points on the Normandy coast. This allowed for an immediate bypass of damaged port infrastructure, preventing the critical bottleneck that German planners had so confidently predicted. The challenge of laying these first lines was immense. It wasn't the relatively calm conditions of trials. This was the chaotic, dangerous environment of a live invasion zone. The English Channel was still a contested space, with mines, U-boats, and Luftwaffe reconnaissance aircraft posing a constant threat. The seabed off Normandy was riddled with obstacles, from sunken ships to unexploded ordnance. Yet, Force Pluto, working with remarkable precision and courage, began the delicate operation. The first HAIS cable was successfully laid on August 12, 1944, connecting the Isle of Wight to Cherbourg, followed swiftly by others. The longer, larger capacity Hamel pipelines, requiring the massive conundrum drums, started coming online soon after. The immediate impact of these operational pipelines was profound. They began to pump hundreds of thousands of gallons of fuel directly to the waiting Allied armies. This continuous flow of petroleum freed the invasion forces from the tyranny of the tide and weather, which constantly disrupted conventional tanker deliveries to beachheads. It eliminated the need for countless individual tanker trucks traversing the war-torn countryside, risking enemy fire and straining an already overstretched road network. Instead, the fuel arrived steadily, reliably, and most importantly, invisibly. For German intelligence, the sustained Allied advance across the Normandy countryside was a source of growing bewilderment. Their reports had consistently highlighted the critical dependence of a modern army on fuel and the impossibility of rapid, large-scale supply without deep water ports. Yet, the Allied mechanized divisions, particularly fast-moving units like Patton's Third Army, continued to push inland with astonishing speed, seemingly unaffected by the predicted fuel shortages. German commanders could not understand how the Allied logistical tail was being maintained. They searched for massive convoys of fuel trucks, but these often seemed disproportionately small compared to the combat units they supplied. They knew Allied ports were either still captured or unusable, yet the fuel continued to flow. The answer, hidden beneath the waves, was beyond their comprehension. The idea of laying vast, high-pressure pipelines across the channel, directly to the front, was simply too audacious, too complex, and too technically advanced for their tactical imagination. They had dismissed such a concept as infeasible, or even fanciful, early in the war. Now, their underestimation was proving to be a fatal blind spot. Pluto had passed its first major test. From a daring concept in secret labs to a functioning reality on the battlefields of France, it was proving its worth. The invisible lifeline was now pulsating beneath the channel, defying enemy expectations and providing the crucial energy that would propel the Allied armies off the beaches and into the heart of occupied Europe. This silent, steady stream of fuel was the logistical linchpin, turning the tide from a tenuous foothold into an unstoppable advance. Once the beachheads were secure and the initial pipelines, tombolas, demonstrated their viability, Project Pluto transitioned from emergency deployment to its full, staggering operational scale. The vision was to establish multiple, more robust pipeline systems, known as Operation Dumbo, due to their greater capacity, to ensure a continuous and overwhelming flow of fuel. The primary target for these permanent lines was the critical port of Cherbourg, once it was finally cleared and available. The task of laying these main lines was monumental. The conundrums, those colossal floating spools holding miles of Hamel pipe, became a familiar, if still highly secretive, sight in the channel. Tugs, manned by Force Pluto crews, embarked on daring voyages, slowly unwinding the steel pipes onto the seabed. By September 1944, a total of 17 operational pipelines were running across the channel. These were not just single lines, but a complex, interconnected network, ensuring redundancy in case of damage and maximizing throughput. The numbers tell a compelling story of Pluto's impact. By the end of 1944, Pluto was delivering an astonishing over 1 million gallons of fuel per day to the Allied forces on the continent. In total, between August 1944 and the end of the war in Europe, Pluto successfully delivered approximately 172 million gallons, over 780 million liters, of petroleum products to the Allied armies. This was a staggering achievement, equivalent to thousands upon thousands of individual tanker truckloads, each vulnerable to attack and logistical delay. This continuous, unseen river of fuel was absolutely vital for the rapid Allied advance following the breakout from Normandy. Generals like George S. Patton, renowned for his lightning-fast armored thrusts across France, were famously aggressive in their pursuit of the retreating Germans. Such rapid movements were utterly dependent on an equally rapid and massive fuel supply. Pluto provided this. While Patton's units still faced local shortages and relied on audacious logistical feats like the Red Ball Express, Pluto delivered the foundational bulk fuel that made these operations even conceivable. It meant that critical fuel could be moved directly from England, through the pipes, into forward distribution points, and then quickly to the advancing armies, rather than being painstakingly ferried across the channel by ship, offloaded, and then transported by truck from damaged ports. German intelligence, as the Allied advance gained unstoppable momentum, grew increasingly baffled. Their earlier analyses had assured them that the Allies would eventually grind to a halt due to fuel shortages. They observed the destruction of ports, the strains on road and rail networks, and yet, the Allied tanks and trucks kept moving. High-ranking German officers expressed confusion and frustration. How were the Americans and British maintaining such a rapid, fuel-intensive offensive? Some hypothesized that the Allies were finding secret, untapped oil reserves in France, or that their rationing was far more severe than imagined. The true answer, lying beneath the waves, remained largely an enigma to them. This invisible lifeline fundamentally altered the logistics of the Western Front. It provided a dedicated, resilient, and virtually undetectable source of bulk fuel that completely bypassed the expected bottlenecks. It meant that the strategic planners in London and Paris could count on a constant, predictable flow of the lifeblood of their armies, allowing them to plan audacious encirclements and rapid breakthroughs without constant fear of running dry. Pluto was more than just an engineering marvel, it was a strategic enabler. It transformed the logistical challenge from a potential invasion stopper into a manageable, and, ultimately, an overwhelming Allied advantage. By providing the fuel that powered the tanks of the Third Army across France, the trucks of the Red Ball Express, and the fighter bombers overhead, Pluto ensured that the momentum gained on the beaches of Normandy was never lost, driving the Allies inexorably towards the heart of Germany. It was the silent, steady pulse that kept the war machine thundering forward. While the Allied armies surged across France, their mechanized columns devouring territory and vast quantities of fuel, German intelligence remained largely in the dark about the true source of this relentless energy. Their initial assessments of D-Day's logistical challenges had been shrewd, accurately predicting the severe difficulties the Allies would face in securing and operating deep-water ports. They had factored in months of delays for port repairs and expected the Allied advance to be constrained by a crippling lack of fuel. Yet, the reality unfolding before them defied all their logical military calculations. Reports from the front lines and aerial reconnaissance showed a puzzling discrepancy. Allied forces were moving at a furious pace, conducting fuel-intensive operations with tanks and trucks, but there were no corresponding massive convoys of fuel tankers offloading at ports, nor were vast numbers of vulnerable road tankers visible in transit, which should have been easy targets for the Luftwaffe. German high command, including Hitler himself, repeatedly questioned how the enemy was sustaining such a colossal consumption of petroleum. Their frustration grew as their own panzer divisions often stalled for lack of fuel, while the Allies seemed to possess an inexhaustible supply. The answer, Project PLUTO, was a secret so profoundly kept, and a concept so audacious, that it simply fell outside the scope of German strategic and technical imagination. Early in the war, the idea of flexible pipelines across the Channel had been dismissed by German engineers as impractical, too vulnerable, or simply impossible given the materials and technology they believed the Allies possessed. This early, confident dismissal created a crucial blind spot that persisted throughout the invasion. German intelligence continued to search for conventional explanations for the Allied fuel bonanza. They theorized about hidden fuel dumps, severe rationing within Allied ranks, or an unprecedentedly efficient, yet unseen, system of surface tanker shuttles. They meticulously monitored every port, every rail line, and every major road. But the invisible lifeline beneath the waves remained precisely that, invisible. The low-profile HAIS cables were often mistaken for ordinary submarine telegraph cables if spotted at all, and the Hamel pipes, once laid, settled onto the seabed, blending into the environment. This oversight was a testament to the effectiveness of Allied deception and, more fundamentally, to a psychological barrier in German thinking. Their technological prowess in certain areas was undeniable, but they struggled to conceive of certain forms of innovation, particularly those aimed at overcoming basic logistical hurdles through unconventional engineering. They were confident in their own assessment of what was possible, and therefore dismissed anything outside that framework. The result was a continuous, agonizing bewilderment that contributed significantly to German strategic miscalculations. If they had known about PLUTO, they might have diverted precious U-boats or sabotage teams to attack the pipelines, or aerial reconnaissance to identify the disguised pumping stations. But they didn't. They were fighting a phantom logistical battle, constantly trying to solve a problem that, for the Allies, had already been solved beneath the sea. PLUTO was a triumph of intelligence and counterintelligence, not just for its operational success, but for the depth of deception it maintained. It stripped the Germans of a vital piece of information, preventing them from attacking a critical vulnerability. The pipeline operation thus became a silent, unseen force multiplier, ensuring that the Axis powers remained strategically blind to a fundamental aspect of the Allied war effort. As the Allied armies pushed further and further inland, their tanks and trucks guzzling fuel as if from an endless spring, German generals could only shake their heads in frustration, unable to comprehend the silent, steady flow of the invisible lifeline. Their fatal oversight cost them crucial opportunities to disrupt the Allied momentum, and ultimately, contributed to their defeat. The liberation of Europe, a triumph forged in blood and sacrifice, owed a significant, yet often overlooked, debt to the audacious success of Project PLUTO. By the time of the German surrender in May 1945, the invisible lifeline had pumped an astonishing 172 million gallons of fuel from England to the battlefields of France. This staggering volume, delivered relentlessly and often undetected, was the silent, pulsating heartbeat that sustained the Allied war machine, enabling the rapid advances that ultimately crushed Nazi Germany. PLUTO's impact was multifaceted and profound. Strategically, it completely negated Germany's most confident prediction about the D-Day invasion, that the Allies would be crippled by a lack of fuel without functioning deep-water ports. By bypassing destroyed port facilities and vulnerable surface tanker convoys, PLUTO ensured that the Allied armies, from the beaches of Normandy to the heart of Germany, never ran dry. It allowed for the unyielding momentum that characterized the push across France and into the Reich, preventing the bogdown that German planners had so eagerly anticipated. Without PLUTO, operations like Patton's lightning thrusts would have been logistically impossible. Operationally, PLUTO was a logistical marvel. It saved countless hours of manpower, fuel, and vehicles that would otherwise have been dedicated to transporting petroleum by road or rail. It freed up thousands of tanker trucks and their drivers for other vital supply roles and reduced the strain on fragile infrastructure in the immediate aftermath of the landings. Furthermore, it minimized the risks to shipping from U-boats, mines, and air attacks in the Channel, as the bulk of the fuel was flowing safely and secretly beneath the waves. The enduring legacy of PLUTO is a testament to the unsung heroes of wartime ingenuity. This wasn't a story of generals leading charges or pilots dogfighting in the skies, but of brilliant engineers, tireless factory workers, and dedicated naval crews. It was a story of boffins who dared to think beyond conventional boundaries, transforming a seemingly impossible challenge into a tangible reality. They developed entirely new manufacturing techniques, invented specialized laying vessels, and engineered complex pumping systems, all under immense pressure and extreme secrecy. For German intelligence, PLUTO remained a mystery until late in the war, if fully grasped at all. Their underestimation of Allied engineering capability, and their rigid adherence to conventional logistical assumptions, created a fatal blind spot. They were baffled by the sustained Allied fuel supply, searching for solutions in the wrong places, while the lifeblood of the invasion flowed quietly beneath their noses. This profound oversight highlights the crucial role of intelligence and counterintelligence in modern warfare, demonstrating that victory is often won not just by superior firepower, but by superior information and the ability to maintain crucial secrets. The story of PLUTO serves as a powerful reminder that victory in total war is a complex tapestry woven from many threads: the courage of soldiers, the brilliance of commanders, and crucially, the quiet triumphs of science, engineering, and logistics. It illustrates that seemingly mundane problems, when solved with audacious innovation, can have the most monumental strategic consequences. The pipes, once laid, continued to serve, even after the war, a silent monument to an extraordinary feat. The invisible lifeline of PLUTO was a symbol of the Allied determination to overcome any obstacle. It fueled the thunder of the invasion, bewildered the enemy, and played an indispensable role in ensuring that the D-Day landings translated into the swift and decisive liberation of Europe. It was a triumph of unseen ingenuity, proving that sometimes the greatest victories are achieved not on the battlefield, but deep beneath the waves, in the realm of the truly audacious and the utterly secret.